Hi there, students. This is Mrs. Brunk. Welcome to the next unit on quadratics. So we just finished studying about graphing quadratics, and we looked at different ways that quadratic functions are expressed, like standard form and vertex form. And we even talked about converting from one to the other using a method called the completing the square method. But now we're going to be moving into another aspect of quadratics that's focusing on solving quadratic equations. And we're going to be looking at multiple different ways to solve quadratic equations. And our goal is to try to know multiple ways so that depending on the type of quadratic equation we have, we can pick the best one. So we're going to be building some tools for our quadratic solving toolbox. And quite honestly, today's lesson, the method that we're going to learn about today, is not really a method you would probably, be one of your main choices. It really is just to kind of introduce you to what the concept of a solution to a quadratic is through graphing. So we're going to be looking at the graphing method to solve quadratic equations, but there are definitely limitations to something like that, because quadratic equations, very rarely will have real nice, easy integer values that you could just tell by graphing. So just kind of keeping that in mind. So solutions to a quadratic equation. The solution to a quadratic equation are the points at which the function intersects the x-axis. So if you were looking at the graph, you would look to see where does the curve, the parabola, cross the x-axis, and that would represent a solution to the quadratic equation that's related to that function that we graphed. The solutions are often called other things. Like we refer to them lots of different ways, but they all really mean the same thing. They're called roots. So they'll say the root of the equation. They call them x-intercepts for obvious reasons. We just talked about it's where they cross the x-axis. And you'll also hear them referred to as zeros. So you've got solutions, you've got roots, you've got x-intercept. All of these they all mean the same thing. And there's really three different scenarios that can occur. The first scenario is if we had two solutions. So what two solutions would look like would be the graph would cross the x-axis two times. So for instance, something like this. There's a parabola that crosses twice. There's an example of a two-solution quadratic. You could have one solution, and one solution would look like this. It would mean that the vertex would have to sit right on the x-axis. And we're going to find out that quadratics that have exactly one solution are a special kind of quadratic that we've actually spent a little time talking about. And what about no real solutions? So if we had no real solutions, what we're essentially saying is the graph never crosses the x-axis. So maybe it's a parabola that's has its vertex below the x-axis and opens down. Or maybe we have a quadratic with its vertex above but opens up. So then it would never cross the x-axis, and that would be considered to have no real solutions. We're going to learn later on that those are imaginary or complex solutions for quadratics. So again, we said the method we're going to use today is to try to solve these by graphing. So we'll try to graph these quadratics and see if we can tell where they cross the x-axis. Now when I think about graphing this first one, remember this is in standard form, and in standard form what we usually do is we create a table of values, and in the middle of our table we put the vertex. And how we find the vertex is we'll find the x-coordinate of the vertex by using the little formula, the opposite of b, so the opposite of 2 over 2a, which means 2 times 1 here. So that's negative 2 over 2, which is negative 1. So we'd maybe put negative 1 in the middle of our table. Then we'd take negative 1 and substitute it back into the function. So that would look like this, negative 1 squared plus 2 times negative 1 minus 3. So let's see, that would be 1 minus 2 minus 3, which is negative 4. So we have our vertex at negative 4. We plot that point. That means also the x of symmetry is at negative 1. So right here where that looks like it didn't show up very good on here, this is where the x of symmetry would be. And the vertex then would be on this line at, let's see, negative 1, negative 4, which would be right here. And we know this parabola would open upward, right? But so maybe we would take and find some more coordinates. So we would put a few x values that are below negative 1, say negative 2 and negative 3. And we'd put some that were above, say at 0 and 1. And we would substitute those in, and maybe we'd even use our calculator to help us out, and I did that. So using my calculator to help me fill this in, when I substituted negative 2 in, I got negative 3. So that means when I substitute 0 in, I'll get negative 3. Plus we know that y-intercept right here is negative 3, right? And then if we substitute negative 3 in, my calculator says the output would be 0. And if I substitute 1 in, then I know, because the symmetric nature of parabolas, it would also be 0. But also I could just go ahead and plug that in and see that. So remember we said that another way to refer to a solution or an x-intercept is a 0. And what we really mean is when the value of the function is 0. And so actually in our table right here, we can see the two solutions. They are at the ordered pairs negative 3, 0, and 1, 0, which means that the solutions are negative 3 and 1. And so if we graph these points, let's see, so we have negative 2, negative 3, so there's one point there, and then at 0, negative 3, and then at negative 3 we're at 0, and at positive 1 we're at 0, and we get a parabola that looks just like this. And so right there are our solutions. Our solutions are the x-intercepts, or those zeros, the place where the graph has an output of 0. And so another way to say that, what we'd say is x is equal to, the solutions are x equals negative 3 and x equals 1. Or as an ordered pair, we'd write it as negative 3, 0 and 1, 0. So those are our solutions, our zeros, our roots of the equation using graphing. Okay, so they will give us a little line to put our answers over there. Let's take a look at another one. So I always start with finding my axis of symmetry if it's in standard form. So that's going to be the opposite of b. So it's opposite of negative 10, which is 10, over 2a, which is 2 times negative 1. So that's negative, opposite of negative 10 is positive 10, excuse me. So that's 10 divided by negative 2, which is negative 5. And I can make my little table. I've got negative 5, negative 4, negative 3. I usually go the other way. Sorry about that. I don't know why I did that. I usually put the negative 3, negative 4 on this side. The bigger ones above, but it doesn't really matter. Negative 6 and negative 7. Then I type this in my calculator just to save my time of having to actually type all these in, and I'll tell you what I got. So when I substituted in negative 5 and to find that vertex, I actually got 0. So that right there was the vertex. But remember what we just said? If the output is 0, then that is the solution. And so it looks like the vertex is a solution. Well, when we substitute in negative 6, we get negative 1. Negative 7, I got negative 4. And this is my x and this is my f of x. And then when I plug in negative 3, then of course you see, that's symmetry, so you'll get negative 1. Plug in negative, I have these flip-flops, sorry. Wow, I'm just not doing so hot with these today. Sorry, there, that's better. When x is negative 4, y is -1, and when x is -3, it's -4. So that makes sense because this parabola we know is going to open down, but if the vertex is at -5 and that y, or that x of symmetry is -5, 1, 2, 3, 4, 5, that's right here. And if that's actually the vertex, that's the one point that's actually going to hit that x-axis. There's no way it can ever hit again because remember the vertex is either the highest or the lowest point. And so these other points, let's see, so if we plotted -6, -1, that would be there, -4, -1, -7, -4 would be there, and -3, -4, and that parabola looks like that. So there's that one we talked about that just has just one solution. It's right there at x equals -5, or written as an ordered pair is -5, 0. So this one has just one solution. So let's make this one a you try question. And so go through your normal routine for graphing standard form, find your x of symmetry, the rest of your vertex, and create a table that has some points on either side, and see if either from the table you can tell what the solutions are, if there are any, or maybe from the graph if you don't find them in your table. So go ahead and pause the video now and try number 3 as a you try question. And by the way, that's my dog snoring. Here she is again. All right, so thanks for giving that one a try. As you probably already discovered, there are 2 zeros to this function, and they are at 2, 0, and 4, 0, or x equals 2 and x equals 4. And that vertex was there at 3, -1, and had 2 nice integer solutions at 2 and 4. So now the homework that goes along with this is pretty short. It's just one page. And so what I'm going to ask you that you do is any of the note questions that we don't complete, I'm going to ask that you finish them for homework. And number 4 was one of these. So we're going to designate that as like a you try question. So you'll just do this one on your own as part of homework. And then so I'm going to put in parentheses homework. Okay, so it's part of homework. And then we're going to kind of just, I'm going to pick a few more out that are a little bit different just to give you a taste of some other scenarios you're going to see. And number 5 is one of those. So we're going to go ahead and do number 5 together. And so when you look at number 5, that is not only in standard form, but it's also in vertex form, right? This is in vertex form because you can read right from the equation that the vertex is at 0, -9. You can tell that it's there's no slide left or right, and it's a slide 9 down, right? But at the same time, it's also is technically in standard form, and but you know, and we certainly could do the x of symmetry by doing the opposite of b over 2a, but it would be 0, and then substituting 0 in, you'd see we'd get that y coordinate of -9. So this graph actually crosses, or actually is on the y-axis down at -9, so that'd be right here. So if we were going to pick other points to plug in, we'd say substitute -1 and -2 in, and 1 and 2. And if we substituted, say, 1 in, 1 squared is 1, and 1 minus 9 is -8. And if we substituted in -1, we'd get the exact same thing, because -1 squared is also 1, and then minus 9 is -8. If we substituted 2 in, 2 squared, that's 4. 4 minus 9 is -5. And if we substituted -2 in, we'd also get the same thing, right? So we see that repeating of the y-coordinates. So plotting some of these points, we'd be at -1, -8. That would be right here. We'd be at 1, -8, which is there. At -2, we'd be at -5. And also for +2. And so our parabola looks something like this, and then it's going to continue up, and it's going to cross the x-axis approximately there. And if we don't see that in our table and we had to kind of guess and check, it looks like these cross right here at -3 and at +3. And let's just test it. Let's see if we plug -3 in. If we substitute -3 in for x, that would be -3 squared minus 9, which would be 9 minus 9 or 0. And the same thing with 3. And so, in fact, even though we didn't see it in our table, we actually can see that our two solutions are x equals 3 and x equals -3, or as an ordered pair, they'd be 3, 0 and -3, 0. So notice that these solutions are exact opposites of each other, and that's always going to happen when your vertex is on the y-axis. So when there's no shift left or right, okay, then the graph is symmetric about the y-axis, and therefore the solutions are going to be symmetric about the y-axis and therefore be just opposite signs of each other. So anytime we don't have a middle term, don't have the b, and we have a graph that's actually on the y-axis as its vertex, then you're always going to have that scenario where you'll have your solutions just be opposites of each other. Okay, so number 6 looks a little different as well. I mean, it's only got 2 terms, and specifically the term that's missing this time is the c. And if you remember what we learned about the c, we learned that the c was really the y-intercept. So we know that right away this graph is actually going to cross the y-axis at 0. Well, that means it's also on the x-axis, right? And that means that's one of our solutions. We can tell that already, but maybe we would have started off just finding the x of symmetry. So that's x equals the opposite of b, so opposite of 6 over 2 times a. And that gives us -6 over 4, which reduces to -3/2 or -1.5. So we've got a -1.5 for our x coordinate of vertex, and our x of symmetry then is here at, let's see if I can fit that in there, right about there. Right? So if we actually already know that one of the solutions is there at 0 because that happened to be the y-intercept, you can kind of already tell then that if we go the exact same distance on the other side, which would be another 1.5 units to the left, if we had to predict, we could predict that the other solution was here at -3. But we can go ahead and create our table so that we can verify that. So if I put my x coordinate at -1.5, and I substituted -1.5 in, let's see what we get when we do that. And I got -4.5 for the rest of the vertex. So that would be, let's see, -1.5, and then -1.5, or 4.5, so that's 1, 2, 3, 4.5. So right there, just about. We know that if we say, let's say we plugged in -2 and -1, those are points on either side, and then maybe -3, and 0. Okay, so if I plug in -1 into that function, let's see, save some time, put that in my calculator table. I got -4 when I substituted -1, and I got -4 when I substituted in -2. When I substitute in 0, I get 0, and when I substitute -3 in, I get 0. So just as I kind of predicted, because of that idea of symmetry, because the y-intercept was at 0, but then on the exact other side of the x of symmetry was the point -3, 0. So those are our two solutions, are at -3 and at 0. So let's finish graphing this. So let's see, -2, -4 would be right here, and then the other one at -1, -4, and the graph looks like this. And so our two solutions are right here, x equals -3, or, oops, let's see, -3, and then another way to say that is the ordered pair, and x equals 0, or 0, 0. And that actually is going to be the case that we'll always have 0 as one of our solutions, or our zeros, or our roots, or whatever you want to call them, right? When we don't have a c, okay, when we don't have a constant term on our quadratic, that means that one of the solutions is at 0, because that's, of course, where the y-intercept is, and that and therein becomes the x-intercept because it is at that, at that spot at the origin there. Okay, and how about number 7? So let's see, we always want to start off with our x of symmetry. The x equals the opposite of b, so it's the opposite of 8 over 2 times negative 1. So that means it's at negative 8 divided by negative 2, which is positive 4. So my x of symmetry is at positive 4. So let's see, over here at 1, 2, 3, 4, this is 4. X equals 4. And then if I were to take 4 and substitute it in to my function, let's see what I got. When I substituted 4 in, I got negative 1. So 4, negative 1 would be right here. So let's think about this graph. So this graph is a parabola that opens downward because of the negative a right here, right? So it's saying it's going to open downward. But the vertex is actually below the x-axis. So this thing's going to open down, and even no matter what other coordinates I get, I know it's going to look something like this, right? Even if I don't put specific coordinates on there. And my goal of this question was to find the solutions, and I can tell there are no real solutions. So I could say no real solutions. Now when we learn other ways to solve quadratics, we'll actually be able to find imaginary or complex solutions to this equation right here. We'll probably come back to this exact one and solve it. We're going to find out that in fact it crosses an imaginary axis, so there's imaginary or complex solutions, but it doesn't actually cross the real axis or the x-axis. So we have to say there are no real solutions. And with graphing, we don't really have a means of telling the imaginary solutions. And that's why I guess if we, like I said at the beginning of the lesson, if we had to choose a method, graphing is probably the last one. And also these were kind of contrived examples where, the graph was always crossing on some nice integer values. Of course, that's not always going to be the case for quadratics. So it is important that we look at this method because it gives us an idea of what we mean when we're saying solutions. We're talking why we sometimes call them zeros or x-intercepts. And later on when we look at other methods, then we'll maybe understand why we call them roots, okay, or solutions. All right? So that actually does it for today's lesson, and we'll continue learning other methods, but for today we're going to focus on the graphing. So thanks for coming to class.